Welcome back, focused learners, to today's explainer. We've got a truly wild journey ahead of us. We are going to take some of the absolute densest, most abstract concepts in algebraic geometry and translate them into a clear, concrete mathematics tutorial. We're talking about decoding the Adelic Langlands proof of Hilbert's 15th problem. If you're the kind of person who loves seeing how discrete, clunky geometry can map perfectly onto smooth, continuous, quantum-level fields, well, you are in for an absolute treat today. Let's get right into it.
Here is our roadmap for the explainer. We'll start with a refresher on Hilbert's 15th problem, move through the Adelic Langlands translation and the Satake Trace Identity, then cover smoothing with Fourier Mukai, fixing anomalies at bad primes, and finally, wrap it all up with the universal rigidity proof.
All right, part 1, Hilbert's 15th problem.
So, you already know David Hilbert's 15th problem asks for a rigorous foundation for Schubert calculus. It's that classic branch of algebraic geometry dealing with counting intersecting objects, like lines or planes in projective space. And hey, classical Schubert calculus works beautifully, perfectly even, over complex numbers. But to actually solve Hilbert's problem, we need a rigorous foundation that holds up over arbitrary fields and arithmetic settings. That's the real challenge here.
And this contrast perfectly illustrates our core issue. Think about classical Schubert calculus over complex numbers. Geometric intersections are incredibly smooth and continuous, right? But the second we extend this globally and reduce those intersections to discrete, p-adic, or finite fields, the geometry literally fractures. The symmetries break down entirely, and you start getting these pathological singular behaviors. So our fundamental challenge is figuring out a foundation that actually survives this fracture.
Moving right along to part 2, the Adelic Langlands translation.
The absolute crucial point here is that we are essentially building a brand new mathematical dictionary. We're translating the broken, unstable language of classical geometry into the universally stable language of spectral algebra. For example, the classical Grassmannian manifold, that becomes the Beilinson-Drinson-Grassmannian over the Adel ring. The geometric intersection theory itself transforms into the spectral composition of perverse coherent sheaves. We're basically treating rigid shapes as interacting wave frequencies. It's a total paradigm shift.
Let's actually look at the math making this happen. Treat this equation as our main protagonist today. Up top, we have the classical geometric realm, Schubert varieties intersecting in the Chow ring, which generate those little C variables you see, the Littlewood-Richardson coefficients. But follow the logic down into the Adelic spectral realm. Those exact same coefficients map flawlessly into the exact fusion rules of the local Hecke operators at a point x.
Let's slow down for just a second and step through these variables, because this is the absolute core of the framework. On that first line, we have the geometric intersection of Schubert varieties. Next line down, we have the composition of local Hecke operators. And the third line reveals the magic. Those combinatorial Littlewood-Richardson coefficients, they aren't just counting points on complex varieties anymore. They are now calculating exact automorphic multiplicities.
Which brings us to section 3, the Satake Trace Identity.
Now, what's really wild here is how the Satake Isomorphism acts as a complete bypass for our geometric instability. You see that SPI mapping the local p-adic operator algebra over to symmetric polynomials? Because of this specific routing, it doesn't matter how singular or pathological an intersection space looks. Its arithmetic weight is strictly governed by the dual group representation. It effectively linearizes the entire problem.
Let's isolate this massive formula for a second, the Hecke-Schubert Trace Identity. Look at the equivalence. On one side, we are applying the Grothendieck-Lefschetz trace formula to the L-adic compact cohomology group. But then check out the other side. It beautifully collapses into something purely algebraic. It becomes the Schur character of a complex Lie group evaluated at local Satake parameters.
Okay, let's explicitly define what's at play in that equation. We've got HCM, our L-adic compact cohomology group. We have the absolute value of lambda, which dictates the complex dimension. Then, and this is crucial, we have S lambda, the Schur character of the dual group. That right there is what provides our topological protection. Finally, the alpha parameters are local Satake parameters. Because these Satake parameters are locked firmly onto the unit sphere, that geometric intersection count is completely fundamentally rigid.
Let's keep zooming out. Section 4, Smoothing with Fourier Mukai.
Think of the Fourier-Mukai transform as a sort of algebraic prism. You start out with this discrete, highly localized data sitting as skyscraper sheaves on the dual torus. But as that data passes through the Fourier-Mukai kernel, it undergoes what we call Adelic decompression. It gets smoothed entirely out into stable, continuous wave-like configurations, global homomorphic line bundles.
Now, focus your attention on the right side of this inverse Fourier-Mukai equation. We are taking our discrete intersection data, those C variables acting as our exact frequency markers, and we are literally distributing them across the continuous spatial coordinates of the prim fiber, which is represented here by the exponential function.
Let's check out the variables to see exactly why these newly formed wave packets are stable and cannot distort. We have V for the torus volume and Y for the continuous spatial coordinates. Those discrete integer multipliers, our intersection counts, are permanently bound to the quantized winding numbers of these fields across the canonical pairing. Universal rigidity in action, right there.
But what happens when things inevitably break down? Section 5. Fixing anomalies at bad primes.
So, here is the step-by-step anatomy of an arithmetic degeneration. First, under reduction modulo p, the geometry fractures and the prim fiber torus just collapses. Second, the inertia group activates, and we get this wild Galois ramification. Think of it as a massive turbulent phase scrambling effect, which flattens the local L function. And finally, step 3, we get a sharp conductor jump, where the Artin and Swan conductors spike dramatically to reflect that massive phase scrambling depth.
This sequence is exactly the nightmare scenario Hilbert was worried about. Over a bad prime, the intersection variety can literally collide paths. It can drop in dimension, or acquire completely unexpected multiplicities. We run a very real risk of catastrophic informational loss here, unless, of course, the universe has a built-in microlocal stabilizer.
And here is how the math miraculously fixes it. Look at the local phase correction. The local epsilon factor basically acts as a fault-tolerant pressure valve. It rotates to absorb the geometric irregularity. Now check out the Lagos stress-energy tensor equation. Notice the delta function strictly isolating the stress to the p-adic point source. What this equation proves is that the physical mass energy of the arithmetic defect perfectly counterbalances the total ramification depth of the geometric singularity. It's self-correcting.
Which brings us to our final stop, Section 6, the universal rigidity proof.
This is the absolute climax of the entire framework. We are looking at the global product formula manifesting directly inside the geometry. For the global automorphic representation to remain stable, the product of all local epsilon factor phases simply must equal 1. This means if a singularity at a bad prime tries to alter the count, it triggers an instantaneous, exact counter-rotation at the continuous complex canvas, the Archimedean place. It mathematically locks the global intersection number in place.
So why does all of this matter? What's the big takeaway for you today? Simply put, Hilbert's 15th problem is solved. The number of intersecting lines is perfectly identical whether you compute it over smooth complex numbers or highly discrete finite fields. The count is completely protected by the structural stability of the global Adelic Hecke algebra.
I want to leave you with a pretty wild thought to chew on. If algebraic geometry is genuinely this universally rigid and self-correcting at the quantum arithmetic level, are the intersecting lines we observe in projective space simply the macroscopic shadows cast by a perfectly balanced Adelic field flowing through the very fabric of our space-time? I highly encourage you to explore the Adelic Langlands program further to find out. Thanks for joining me on this explainer, and until next time, keep learning.